Hello and welcome back to part 2 of our video on dispersion forces. So this one we're going to specifically be looking at dispersion, which is considered to be the basic force of all compounds. We're going to try to understand what the concept of polarizability is and how this has an effect on different intermolecular properties. So where does this all start with? Well, when we look at all these, this is the dominant force for things that are nonpolar. So things like noble gases, nonpolar molecules, but it can be found in all matter, meaning everything has dispersion, but it's the strongest for something like nonpolar. So what is exactly occurring here? Well, it has to do with the electron cloud around all these molecules. So let's say if I look at a helium atom, which is your simplest noble gas, which has 2 electrons. Well, when we are trying to look at this, well, essentially, if the electrons try to disperse themselves from one side to the other, where we see that most of the electrons are all piled up on the right-hand side, this is what makes an instantaneous dipole, or a temporary one. Usually this occurs when things collide with one another, they hit each other, where we have this movement happen. So whenever we see this, this is where we have this dipole. Now, when we're looking at these, let's say if we go from one to the other, and let's say one of them has a dipole and it collides with another atom or another molecule, which is also nonpolar, it can induce even more dipoles to occur where they can have this weak attraction. So if you kind of notice, I had put in the delta pluses, delta minuses, to help like really illustrate how they are actually attracted to one another. But this is temporary. It's something that doesn't last a long time. The electrons will try to push each other away because they don't want to be all bunched up on one side of the cloud versus another. They will go back. But it's long enough for there to be maybe a liquid could form, maybe a solid could form for a brief moment, or if it's cold enough and they're moving slowly enough for this to happen, where there's not a lot of energy for this to actually occur. So to really show this, where does this apply to when it comes to things, is in the boiling point and melting point of compounds. So here in what I'm going to show here is going from temperature. So we go from cold to hot. So red being hot, cold being blue. If we were to put things like methane, which is CH4, it's a very simple organic compound. And if I were to increase the size of the molecule to, let's say, benzene, or sorry, not benzene, but hexane, which is C6H14, we have a 6 carbon difference with a lot more atoms. We can see that the temperatures for the boiling point goes up by almost 200 degrees, and we're only adding a few more atoms. So there's a massive difference for nonpolar molecules the more and more you add. So every atom is going to make a difference. So one thing you can ask yourself is, well, which one has the stronger intermolecular force? So the idea here is the stronger the intermolecular force, the more it's going to want to hold it into the liquid phase, right? So boiling point is all about it becoming a gas. So it's like going back to my video in part 1. One of the things about that was, well, if you really were to look, it essentially through that video was the one with the stronger intermolecular force, which was water, took a really long time for that to really break and to really see that happening. So in this case, the higher one, the higher boiling point, is the stronger intermolecular force. So it's more difficult to separate these. So the things that we're looking for is stronger intermolecular force, which is 1. The second thing is the bigger the molecule, the harder it is as well. Those 2 things that we're looking for at all these different molecules. Now, other ways for us to look at the size. Well, let's look at the noble gases. So if we go from the top, which is helium, down to neon, to argon, krypton, to xenon, one thing that you'll see is that the molar mass is increasing dramatically, meaning more electrons, more protons, more neutrons. And also with this, the temperature of their boiling point changes too. Helium is the lowest one, as 4 Kelvin is its boiling point. It doesn't take long for it to become a gas. Whereas if I were to fill in the other ones, right, with neon, argon, krypton, and xenon, you can see that it goes up, 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 up because it's becoming heavier. Those electrons are harder. Essentially, it's a more of an attraction because there's more of them on one side versus another. So the bigger, the more attraction. So when we are trying to look at them, the more molar mass, more attraction. So now this is what we refer to as polarizability is the key word here. So more mass is a larger polarizability, which means that's going to have a stronger dispersion force between the molecules. This is important for general chemistry, introductory organic chemistry to understand how we can predict how chemicals will behave when they're a solid, a liquid, or a gas with all these different substances. Okay, so and you can really see how we have heaviest to lightest looking at all these little individual components. Now, when we're trying to, how can I exactly explain what this means? How does this come about? Well, this whole idea of instantaneous dipole. Well, like I mentioned before, it has to do with the electrons, right? So I listed their electron configuration here and their total electron count. And you can see with helium, right? That was the simplest one, 2 electrons. It had like 4 Kelvin. Whereas xenon has 54 electrons and went to 165 Kelvin. 160 K difference, that's a lot. That's a big temperature shift. So how can we explain this? Well, you have to try to think of what is the probability of all of them being shifted to one side or the other. How long will they stay attracted to each other for? So one way to think of it in a really, really simplistic model is, let's say I take an electron and I treat it like a coin flip, meaning it can either be on the left side or the right side, and that's it. So if I were to try to do the probability of that, well, there's a 50% chance it can go left, 50% chance it's going to go on the right. So if you need both of the electrons for helium to go on one side, well, you have, about a 50-50 chance, a little bit, for them to go on the same side. And you can try to do this for all these different electrons to see, okay, well, where are they going to be? So if I were to say to make them an even distribution, so where I have one electron on the left for helium, one electron on the right, it's like about a 50-50 chance. Now to evenly distribute all the other electrons for, let's say, for neon, from argon to krypton to xenon, it becomes increasingly more difficult to get them to be even between the two sides. So what does that mean is that there's always going to be a little bit of an instantaneous dipole for bigger molecules because it's impossible almost to have it perfect. So you can see xenon, it's like a 10% chance for it to be even, meaning most of the time it's having attraction between other xenon. So, and that's one of the reasons why we are actually seeing that difference. So what is the pattern here in the end? Well, one thing is the more electrons or the heavier it gets, the probability of unevenness goes up. So we will always have this instantaneous dipole for really, really big molecules because it's likely that they're not going to be even. So this is what we mean by polarizability. It allows us to be able to predict exactly what forces we are going to see. So the bigger it is, the higher the melting point, the higher the boiling point, which is really, really important when we're trying to understand how the chemistry works, right? So that is one thing. So bigger, stronger dispersion is one of the things that we are trying to get out of this video. All right, let's take a look at some other ones. So going back to the example from before, right, where I mentioned methane and then hexane, which was 6 carbons. Here I have essentially 1 carbon, 2 carbons, 3, 4, 5, and we can see the temperatures are increasing as well. So if we were to put all those on a chart, as the bigger it gets, the higher it goes. So what can you try to say about that? Well, from heaviest to lightest, the heaviest one has the strongest force of attraction to other molecules of the same type, making them a lot more difficult to separate. So larger molecules have higher polarizability, which makes them have essentially a stronger force of attraction and more likely to be a liquid or even a solid the bigger it gets. One way to think of it too, when it comes to organic molecules like these, methane, ethane, propane, and butane are all gases, right? Propane you find in stoves, or butane you might find in a lighter. It's generally a gas and starts to become a liquid as you go through, depending on how much pressure it has. Whereas, let's say octane, which is what you fill your car with, is a liquid, right? We call it gasoline in the US. it's a liquid. And then the farther and farther you go is when you eventually start becoming a solid, when you add enough of these carbons to the molecule to get more and more attracted to each other as you go. So just to kind of practice this concept, well, predict which one would have the strongest intermolecular force. So I have two molecules here. I have hydrogen and oxygen. Both of them are linear, so meaning they're going to be nonpolar diatomics. Every diatomic is nonpolar, which is one of the most important things to keep in mind. Which one is more? Well, hydrogen, right, is one of your smallest elements. So when we're trying to look at it, right, the first thing you want to do is, are they nonpolar? As I just said, they are. The next thing we're going to look at is, well, let's see if we can figure out the sizes of each one of them. Well, if we want to look at the sizes, well, hydrogen looks like the Lewis structure on the left. Oxygen looks like the one on the right. They look about identical when it comes to electronegativity. So when we look at both of them, right, oxygen has a molar mass of 32 grams per mole. Hydrogen has a molar mass of 2. So it's 2 electrons versus about 16 electrons. That's a huge difference between the two, meaning that hydrogen, the odds of the electrons being even is pretty high, whereas something like oxygen, there's such a big volume here, there's such a large area for the polarizability to occur, that's going to lead to a stronger dispersion force. So oxygen is going to be a lot higher as a result. Okay, so you're looking at which one's bigger is the sum of this. Let's look at this next one. So CF4 and CBr4. Well, fluorine is, so it's pretty much carbon, they're the same size. So fluorine versus bromine. Fluorine is in the top right corner of your periodic table. Bromine's a little bit lower. So which one would have the stronger dispersion force? These are both nonpolar, right? Because they both are tetrahedral geometries. The heavier of the two is going to be bromine, right? So CBr4 is going to have a much larger volume to it. It's going to be more electrons, more dispersion that's going to be occurring, a higher polarizability. So out of these two, the one that's going to be stronger is going to be CBr4 is going to be the key here. Now, to sum up everything we talked about, how do we keep dispersion correct? All molecules do this force. It's considered to be a universal attractive force between all of them. So this is something that they all can do as this temporary dipole is just because electrons are not even between the molecules. However, it's essentially the most prominent force for anything that's non-polar. So whenever we're looking at this, how do we figure out which one's bigger? Well, it's generally based on the number of electrons, which means more valence shells, the larger it is. So we want to look at which one's the biggest of all, what's the heaviest in terms of molar mass. So look at your molar mass, figure out what's the heaviest, and that is going to be your answer. Okay. So now keep in mind though, when you have, let's say, stronger intermolecular forces, they will override dispersion. So if you have something that's polar, that automatically is going to be stronger interaction. So we always look at intermolecular force first, then we look at size afterwards. And that's what we're looking at for intermolecular forces. I hope this video helped you trying to understand part 2 of our video here. So thank you so much for watching, and please stick around for more on intermolecular forces.